So we have this equation now, and in this equation, we can have some common terms which we can cancel out, and this entire formula will be reduced to rho into f double dash of rho, double derivative of rho, uh, with respect to rho, plus 2l plus 2 minus rho into f dash of rho plus lambda minus l plus 1, okay, into f of rho, okay, equal to 0. So we know that we have defined f of rho as a power series. Okay, so this is a power series, and the power series we have already done some problems earlier. Okay, and it can be defined as k is equal to 0 to infinity ck, which is just some coefficient of rho to the power k. Okay, so this is a power series, and you can now calculate using this power series f double dash of rho. You can calculate f dash of rho, and f of rho is this thing itself. So this will be looking like this. So if you have those terms with you, so you can have summation of k is equal to 0 to infinity c of k plus 2, k plus 1, k plus 2, rho to the power k plus 1 plus k is equal to 0 to infinity c k plus 1 2l plus 2 minus rho into k plus 1 rho to the power k plus lambda minus l minus 1 summation of k is equal to 0 to infinity, okay, ck rho to the power k equal to 0. Okay, so here I am having k to the k plus 1. So what I will do is, I will, since k is just a dummy variable, so I will subtract, uh, uh, I will replace k plus 1 to k minus 1. So nothing will happen. This term will actually look like this now. Okay. Uh, this term I am only writing this term. So it will be k is equal to 0 to infinity c of, since I have to subtract so that it becomes rho to the power k. So it will become k plus 1. This will become only k, and this will become k plus 1. And now this term is equal to rho to the power k. Okay, and this term will be same as this, plus this term will be same as this, equals to 0. So what you can do, since all are having the now rho to the power k as their coefficient, so you can equate all of them, and since rho of k cannot be equal to 0, then their coefficient must be equal to 0. So if you equate those coefficients, so equating coefficients of rho to the power k from all terms to 0. So you will be having, okay, c of k plus 1, k into k plus 1 plus c of k plus 1, 2l plus 2, you can see this, Okay, 2l plus 2. Okay, here also you will be having one term. Okay, so you have to do this same thing there also, because it will be row into row of k minus row into k. So it will again make this as k plus 1. So again you have to make it subtract one term, and then you have to make this thing 0. So this will be having k plus 1 minus ck into k. Okay, because this thing 2l plus 2 and k plus 1 will have no problem, they will have the coefficient rho to the power k. But when this thing will be there, this thing and this thing, so there will be an extra term, k equal to 0 to infinity c of k plus 1 uh, into rho. Okay, then there will be a negative sign outside into rho to the power k. So here this term is having rho coefficient k is equal to 0 to infinity c of k plus 1 rho to the power k plus 1. So what I will do, since I have to make it rho to the power k, I have to subtract. So it will be having ck and rho to the power k. So that is how this term comes, and there is a negative sign outside. So this is why this is an extra term appearing here, plus lambda minus L minus 1 into Ck equal to 0. Okay, since this is the thing which we are having, so now we can have the recursion relation. So the recursion relation will be C of k plus 1 by Ck is equal to k plus 1 plus k plus L plus 1 minus lambda is equal to divided by k plus 1 into 2l plus 2 plus k. Okay, so this is your recursion relation, and just having two values of coefficient, you can find the values of the coefficient of all the terms. So you can now have the entire series, where if you have the value of k and k plus 1, then you can have for infinite terms the value of the coefficient multiplied by root k. Okay, so this value can be found out using the recursion relation. So now this is the recursion relation, and it can give you the values of all the coefficient. For k is equal to infinity also it can give you, but you cannot say that it is basically a solution, and this solution cannot go to infinity. So basically we have to truncate the solution, and basically take some maximum value of k, where c of k plus 1 will go to 0. Okay, so I will say, okay, that at some particular value the numerator should go to 0 for some particular value of k. So that value I call k max. Okay, so for k max plus L plus 1 minus lambda, this will be equal to 0 when k is equal to k max. Okay, so I can now find the value of lambda, which is, okay, so in some textbooks this is actually written as nr. Okay, so kmax is basically written as nr. Okay, and they call this as the radial quantum number. Okay, so this is basically your radial quantum number. So I will write this as nr. This is your L, which is nothing but the orbital quantum number, plus 1. So basically this is also a quantum number, this is also a quantum number. So this lambda is generally written as n, which is equal to nr plus L plus 1, where this n is known as principal quantum number. So now we have obtained the value of lambda. Okay, which is equal to n. Okay, so now I have already defined the value of lambda. Lambda was a rescaled parameter. So now let us go to our original things. So this is your value of lambda. Okay, so lambda is defined as minus z alpha, sorry, z alpha into minus mu c square by 2e raised to 1 by 2. So here itself you can see that, okay, since lambda is equal to n, okay, since lambda is equal to n and this is equal to z alpha by minus mu to c square by 2e raised to 1 by 2. So now you can see that I have to find the value of e. Okay, so e will be equal to, okay, minus 1 by n square z square e square, okay? Or let me write this way, okay, z square, okay, or let me rub it all, minus 1 by n square, and there will be a term called mu c square, okay, then there will be a term called z alpha square, okay. So this will be the values of my energy eigenvalues, and I can substitute the value of alpha, okay, and alpha is nothing but, okay, uh, e square by h cross c. So if you substitute this value of alpha and all those things, so you will get the value of energy eigenvalues, okay, equal to minus 1 by n square z square e square by 2a0. Okay, so I have again introduced a variable a0, which is nothing but the Bohr radius. Okay, and the Bohr radius is equal to h cut square by m e square. Okay, so this is the value of the energy eigenvalue. Okay, let me write it downwards. So we have derived the value of E equal to minus 1 by n square z square e square by 2 a0, where a0 is the Bohr radius, okay, and it is equal to h cut square by me square. Okay, so we will stop this lecture here and we will discuss more about the features of this energy eigenvalue in the next lecture.